So, in today's class we will go through a very important derivation for conduction, namely the derivation of the general energy equation for heat conduction problems. Then you can look at simplifications of this general equation and arrive at energy equation for one dimensional steady, two dimensional steady, one dimensional unsteady, two dimensional unsteady. This is basically applicable for three kinds of coordinate systems: Cartesian coordinates, cylindrical coordinates, spherical coordinates. Okay. Since it is easy to derive it for Cartesian coordinates, we will do it only for Cartesian coordinates, and then we will say it can be derived for both the cylindrical and the spherical coordinate system, and we will use, I will write out only the final forms of the equation. Okay. So, the energy equation, the variable, the primary variable for which we write the equation is going to be, what is it? Dependent variable? Temperature. Okay. Though the fundamental quantity of interest may be heat flux in most of the situations, in the last class we have seen that it is easier to measure temperature, and from temperature can be easily related to the heat flux via which equation? Fourier's law of heat conduction. So, if you want to determine the heat transfer in conduction, if you are able to write down a governing equation, partial differential, ordinary differential, whatever equation in temperature, if you are able to solve it and get the temperature field, then at the boundary or wherever you want, you can apply the k dt by dx and get the q. We also saw that the q is a vector, heat flux is a vector which is orthogonal to the isotherm. Temperature is a scalar, but heat flux is a vector. We saw isotherms for the slab, and I asked you to figure out how the isoflux lines will look like, right. So, now we are going to derive the energy equation for heat conduction. Is basically in Cartesian coordinates. So, this is the x, y, z coordinate. So, z is coming out of the blackboard, okay. Z is coming out of the blackboard. I take an arbitrary volume, arbitrary shape which has got a volume V. I am considering an elemental volume dV. The elemental volume is a cuboid with dimensions dx, dy and dz. This body is moving with a velocity which is given by V. V has got three components u, v, w. Sir, why do you want to have a moving body in conduction? I told you welding rod problem or moving heat source problem, or some bullet or bomb, bullet or cannon is fired, that source is also moving, okay, or welding rod is moving. So, we have to derive the heat conduction equation in its most general form, and then in many cases we will say this velocity is 0 and reduce it for the stationary case, because 99% of the time it will be the stationary case, but we should have a general equation to cover the cases where the body is moving. Okay. Now, we have identified dx, dy, dz. Now, we have to identify the various terms which contribute to the law of, and apply the law of conservation of energy to this. Okay. So, we will start this. So, applying the first law of thermodynamics to the CV, the control volume, I am putting E dot, because this is heat transfer, we are talking about rate per second, how much is the transfer, right, that is what we are interested, what is joule per second. So, E dot in, what is it, whatever the energy is coming in plus, no, okay, is that correct? assuming there is no work done across the control volume, otherwise Q minus W is equal to delta E. I am considering only Q and delta E terms. Delta E is the change in the internal energy which is given by E dot stored, okay. E dot in is the energy which is coming in, E dot out is the energy which is going out. The energy which is coming in need not be just only because of the conduction, the body is moving, it can also be because of advection, okay. So there is an incoming energy, if there is no heat generation and steady state prevails, the incoming E dot in must be equal to E dot out, simple, okay. But if E dot in is not equal to E dot out, then the body may be depleted of its internal energy, or there may be an accumulation of internal energy over time, that means the temperature will increase. So there will be a E stored, E dot stored, right. Over and above all this, if there is a chemical reaction or nuclear reaction taking place in the control volume, that will also contribute to the increase in temperature. That is why E dot generated and E dot stored will appear on opposite side of the equation, okay. Are you getting the point? If it is continuously generating heat like the Fukushima reactor, and you are not able to dissipate the heat, what will happen? E dot stored will increase. E dot stored means enthalpy or energy will keep on increasing, temperature will increase, okay. Now the goal is to write down mathematical expressions for each of these terms and convert it into a partial differential equation in temperature, okay. Now it is generic, it is universally applicable, we are not applying any particular rate laws. What?
No, it should be reverse. E dot in plus agent should be E dot out plus.
Is it? It depends on what you want to call E dot I.
Heat is generated and there is no heat in, then there must be heat out.
What?
If energy, if there is a generation of heat and there is no input of heat, then there must be a net output of heat.
I didn't follow. Positively I didn't follow.
Egen is non-zero.
Egen is non-zero, okay.
En is non-zero, is zero, and E stored is zero. E out must be positive. So they have to.
So there are no problems on E in and E out, they have to be on two sides. Everybody agrees that E generated and E stored must also be on opposite sides. Now there is a sign convention, there is a problem whether this must come, how you consider? So what you are saying is E in is coming, E generated is also coming, let both be on one side, okay, fine. So they are positive contributors, okay. So if they are balanced, it will be equal to E dot out, then it will be steady state, but if it is not happening, then it will be E dot stored. Is that okay? I have no problem, even if I put the other way, towards the end I will do some minus plus and I will change it, okay. Okay, if conceptually this is better, you can take it, no problem. Now we will write expressions for each of this. Now E dot x, okay. Where do we write this now? Okay. Now substituting for these terms, we have, yeah, please tell me. Correct. This is shall you write like this, or if somebody writes doesn't like this, you expand. Okay. Plus the heat generation is there, no? Huh? E generation I will call Q generation, Q, huh? So that I know it is watts. Okay. Now we start applying the particular rate laws. So far I have not done anything, I am just doing bookkeeping, I am doing accountancy, I am balancing left side right side, that is all. Okay. Now I have to use my Fundays. Qx plus dx is that correct? 3 Qy plus dx dy okay. Qz yeah. E is different from Q. E is energy. E is energy which is transported because of the motion. The E terms will vanish if the body is stationary. E terms will be the most important terms in your Navier-Stokes equation. I am formulating almost like a Navier-Stokes equation without the viscous Stokes hypothesis. I am not using that. Right? I am following an approach which you will do for deriving the energy equation in convective heat transfer. Okay. Okay. Now this fellow we can remove, na? We will remove this fellow. I can straight away say that the body is stationary, and Vikram, I can straight away say that the body is stationary, and I can give you a very elementary equation. The body can move. Source is moving is an example. Do not think that I am writing the equation for welding rod. Welding rod is an example, that is all. The body whose temperature distribution you want, may be the re-entry vehicle. That body itself is moving. You will say, sir, in that re-entry vehicle it is moving in one direction. Suppose it has got 3 components and there is something like that, then we will take care of the general formulation. Is it okay? Finally, we will knock off all the E, do not worry. Right. Now, what about this? Is that correct? So far so good, right? Now I start doing something. Is it fine up to this stage? So we wrote down simplifying terms for each of these. Let the q dot generate remain. Okay, I will say that I will also say that capital E has units of joules or kilojoule. So small e has units of kilojoule per kg, right? This also we can remove, right? Is it correct? What is dx by dt? U. Very good. E dot, I changed it to E and I brought the time to the x. Okay, so okay. That is not the only thing we are capable of doing, we will do other things. Okay, fine. What is this qx doing here? Don't I have a better expression for qx? Minus k dou t by dou x. Qy is minus k dou t by dou y. Qz is k dou t by dou z. So therefore, huh? Yes. What will be the area? Yeah, people who have some doubt. Okay. This is the Qx. The Qx is passing through this area. That area is dy dz. I did one more thing, I removed the dy dz out of the bracket. I am allowed to do that. Correct? Oh. At this stage, I do not want to pull the k out of the x. Why? I can have a variable thermal conductivity formulation. Correct? If I pull the k out, I am already making a statement that k is independent of x. Many problems it may be like that, but let us keep it like this. Now Qx, what will be this 13? Similarly, you can write an expression for Qz minus z plus dz. Yeah, so we got expressions for each and every term in the energy equation. Go back and substitute all the terms, simplify. Every term will have a dx dy dz, cancel, dividing by dx dy dz throughout, with the understanding that dx dy dz cannot become 0. That is the whole beauty of a finite volume or control volume formulation. They are all valid not at mathematical points, but at engineering points, where each point has a elemental volume associated with this. Okay. Now putting all this, substituting into the, what is the equation number? Ei minus E something, was it 2?
Yeah.
Oh. You are not alert. Qx minus q is minus dou q, and q itself is minus, no? Therefore, this will be plus. You have to be very watchful. Is that okay? We are taking minus dou qx by dou x. Fortunately, the dou qx itself has a minus. So this will be plus. I need that, I have those energy terms. What are those terms? Minus, everything is minus, everything is minus, okay. it is good for us, all the terms have dx dy dz, that also reinforces our belief that we have not made any mistake. Okay. Cancelling dx dy dz throughout. Okay, dividing by is that correct? Hmm? Hmm. If it is too difficult, we will keep it like this now. Next step we will do. Okay. So we will keep it like this, minus yeah, we did not leave any term, right. So what was this number? 16. So this is 17. Any problem, Vinay? Yeah, please feel free. Huh? No problem. Okay. Now, can we make some simplifying assumption? Let us say that the substance is incompressible, so the density is constant. I mean, it is not a great sin we are committing by doing that. Mostly we are dealing with solids. Okay, we are not dealing with gases. Gases anyway, convection will start. So, assuming that the substance is incompressible, so rho is constant, rho can be pulled out. Then what can you say about E? What?
I mean, it doesn't change with space.
Incompressible, it is all encompassing. Whether it is time or x or y, if the density changes, it is not. Okay, it is a necessary and sufficient condition from fluid mechanics. Okay, rho is constant. Therefore, if density is constant, then I can put E goes as h. I can write it as CPT. Very good. It is CT. It does not matter. Specific heat. Okay. Now I can say that or y, Cp also is constant. I can make it minus now tell me V dot no, already we will okay, first we will remove the rho will come out minus rho Cp will come out, u dou t by dou x plus v dou t by dou y, correct, that is it. Okay. People who learn convective heat transfer, you remember that u dou t plus v dou t will be the advection term in your energy equation in convection. It will be the advection term in your, okay. So we can take the advection term to the left hand side. So we can have rewriting now I will apply the master stroke. If the body is stationary, u equal to v equal to w equal to 0, okay. So once you have come to graduate level courses like this, the goal of learning any new subject is basically, you should not try to remember many things. If somebody says what is the energy equation, I forgot, whatever, you give me half an hour I can derive it. Just draw a control volume, find out what are the flux, do a flux balance, and then the key information which you are putting is only one, qx equal to k dou t by dou x, otherwise everything is only thermodynamics knowledge. Then your knowledge of vector calculus and all that, that is it. Then you should be able to recreate or knowledge with just basically you should know only a few things, from that you should be able to build, okay. So now if the body is stationary, so this is a very familiar this is the most widely used energy equation in convection, okay. Which one?
Outside, outside.
Yeah, del dot.
Outside
Sure.
becomes-
Then k or delta will become the scalar one.
Correct. Okay. Finally, it is a scalar vector, no? Which is a vector? Finally, it is okay. Input in qx, qy, qz, it is a vector. Now, let us see. So, the equation 20 is a very formal mathematical statement of the law of conservation of energy, wherein additional information has been injected, which as a thermodynamicist you do not know. The additional information you have incorporated is thermodynamics person is able to recognize this, thermodynamics person is able to recognize this, but this is because you have studied heat transfer, that you are able to put qx equal to k dt by dx. So, when information from particular laws which are applicable to particular media are incorporated into the general equation of conservation of mass, momentum, energy, it leads to the growth of new subjects, okay. So, this is a very formal mathematical statement of the law of conservation of energy. Now, you can see that the net diffusion, the net heat which is conducted in the x, y and z direction plus any heat which is generated because of a nuclear reaction or a chemical reaction must be balanced. In the event of this not getting balanced, then the enthalpy of the body will increase and it will follow rho Cp dt by d tau. Okay, so this is the most general statement where t is a function of x, y, z and time. Okay, so t is a function of now we can look at simpler forms of this. If k is a constant, is it okay? So, what is k by rho Cp? Rho Cp k is alpha. I always ask.
K by rho Cp is alpha.
K by rho Cp is alpha. Okay. Alpha. See, I always try to check it like this. K is watts per meter per. Okay. Watts itself is joule per second. Therefore, when k is in the numerator, second will appear in the denominator. Alpha also has meter square per second. It should be alright unless these fellows are second cube, then we will get RG, but that is a different situation. Generally, it should be fine. So, this alpha is called the thermal diffusivity. The thermal diffusivity gives you an idea of how fast a thermal disturbance propagates in a medium. Okay, if milk is boiling in a kettle and you put a ladle or a spoon, okay, you are trying to stir it and accidentally you leave it, when you touch, within a few seconds you feel the heat if it is a stainless steel spoon. If it is a wooden spoon, it takes a long time. So, the issue there is not because thermal conductivity of steel is more than wood, anyway it is, but even for same thermal conductivity, rho and Cp are different. There the disturbance alpha, the disturbance, thermal disturbance, how far it propagates or how quickly it propagates is decided by the property called thermal diffusivity alpha. So, the thermal diffusivity alpha is a critical parameter only for unsteady heat transfer problems. For steady heat transfer problems, it will be the thermal conductivity which will decide the flow of how much of heat is transferred, the speed with which a disturbance propagates, or for the given time how far a thermal disturbance will propagate. For example, if you have an object like this, now this subhole, this water is at 30 degrees centigrade. Now I keep eyes on this left side. Okay. Now this, the first layers of water which are close to this ice will feel the chillness. Now this thermal disturbance will exponentially decay with time. Okay. So the alpha will decide at a given time how far into this water bottle will the effect of the ice propagate. Okay. If it is alpha is higher, it will propagate faster. If alpha is lower, it will not propagate that much. In fact, later on we will see that the penetration thickness, what will be the units of this? This is the penetration depth for a thermal disturbance. Okay, so it is the product of alpha into now. If the net conduction plus the heat generation is balanced, then there is no rate of change of enthalpy of the material. for steady state conditions, so there is no unsteady term. So this is the unsteady term which gives you the rate of change of temperature with respect to time. There is no unsteady term, therefore we get this is called the Poisson's equation. This is called the Poisson's equation. If q triple prime is also 0, then it reduces to the Laplace equation. Del square is known as the Laplacian, okay, Laplacian or Laplacian operator. It will always operate on a scalar, it will always operate on a scalar. Do you remember any other Laplacian kind of operator in fluid mechanics? Stream function, del square psi, right? And electric potential will come in electrical basic fundamentals of electrical engineering and all, okay, right. Now can you solve the equation right away by analytical method of separation of variables or numerical whatever? What is required to close the problem mathematically? Boundary conditions and initial conditions are required. Initial condition is straightforward, at t equal to 0 equal to t is equal to t specified, or at t is equal to 0 you specify flux. It is only first order in time, okay, so it is parabolic in time. From from t equal to 0 it will propagate, but however there are hyperbolic systems in time, vibrations of a stretched membrane and all that, where it will lead to a lot of problems, but this parabolic in time and it is elliptic in space, okay. People who are mathematically inclined can figure out why it is elliptic in space, reduce the equation of characteristics and find out b square minus 4ac less than 0 equal to 0 greater than 0, all that fine. So now as far as initial boundary conditions are concerned, first kind is basically you say x equal to 0, t is equal to T1, say that is temperature is specified, this is called the Dirichlet condition, okay. You specify the variable directly. Second kind, you specify the information on the derivative of the variable, okay. This is just an illustration, x equal to 0, x equal to somewhere, I can make it very general, x equal to x of s, this thing, I am putting it in a manner which is easy for you to understand. We will say minus k q boundary, Okay. So, this is called the Neumann condition. What will be a special case of this? At x equal to 0, dt by dx equal to 0. What do we call this condition? Heat transfer. Adiabatic or insulated. Because please remember, but you have to be very careful. I have a slab like this, okay. I say this is 100 degrees centigrade. I want a steady state solution. I want a steady state solution to the problem. I am keeping it insulated on all sides. You want to do your BTech project with me, on first day I give you this problem. What will happen to you? Heat is coming from the top, but there is no way for the heat to. So, physically impossible boundary conditions you should not apply. You should know whether it is feasible first. Anyway, quickly you can see everywhere it will reach 100 or whatever. It is basically a difficult system to solve. Are you getting the point? So, if you are applying, if some surfaces are insulated, you have to watch out. If one or more surfaces are insulated, you have to find out whether there is a path for the heat to enter and whether there is a path for the heat to leave. Otherwise, steady state solutions will not come out of the problem. Okay, this is pure common sense. So, the third will be the third kind, where I say at x equal to L minus k dt by dx equal to h into t minus t infinity. What is this? There is a convection which is taking place at the boundary, or I can even say minus k dt by dx equal to epsilon a sigma t to the power of 4 minus 2. That is, it is losing heat by radiation to the outside. This may be some fin system in a spacecraft, something, earth orbiting spacecraft or something like this. Okay. So, this is called as the Robin condition, that is third kind. So, if you write down the governing equation pertinent to your problem, you first identify whether it is temperature is a function of x, y, z and t, or temperature is a function only of x and y or x and t. Write down the proper equation, see whether it is steady or unsteady. If it is steady, initial conditions are not required. If it is unsteady, initial condition is required. Write the initial condition and find out if it is d square t by dx squared alone, two conditions on x are required. If it is d square t by dx squared plus d square t by dy squared, two conditions on x and two conditions on y are required. So, if you have two dimensional unsteady problem, you will have the rho Cp into dt by d tau on the left hand side, right hand side you will have del square t, which involves dou square t dou x squared, dou square t dou y squared. So, you require 5 conditions without which you cannot solve the problem, 1 on time and 4 on space. Once you have this, then you go to the problem and find out, now you take recourse to mathematics. Okay, can I analytically solve it, numerically should I solve it, finite element, finite difference, finite volume, fluent, COMSOL, star CD, I will write my own code, MATLAB, all these things will come. The first is you have to sit down before going to the computer, sit down with paper and pencil, write down the governing equation, conceptually get a hang of the physical system, identify the various boundary and initial conditions. From tomorrow's class, so we will have a breezy start to conduction, we will look at simplified forms of this where we can very nicely come out with analytical solutions. Then slowly I will escalate the difficulty level. Okay.